He's worked on some fairly popular games which you might have heard of and most likely played, such as Assassin's Creed and Rainbow Six. So please join me in welcoming Jeff Preshing.
All right. So hi, I'm Jeff. I work at USF Montreal, and I have a little problem for you. You see, I have this text file containing 10 million 8-letter words, and there are 100 different words in the set. I want to count the number of times each word occurs in the file, and I want it to be fast. So, I've written some C++ code that keeps track of the number of occurrences of each word in a resizable array. So it's just an std vector of items. Each item consists of an 8-letter word. I'll just count. What I do is, for each word in the input, I search the array sequentially, right here, to see if the word's already in the list. So basically a linear search. If the word is found, I increment the count. If it isn't, then I add it. So I timed this code, found that it ran in 3.3 seconds. Now, looking at this code, does anyone have an idea what I can do to improve performance? Shout out to any ideas.
Binary search.
Binary search, anything else? STD set, or you might have meant map, perhaps. That's actually what I tried. Yes.
Use a hash table to sort the words in a specific array.
A hash table. Very good. So I tried both those things. Here's a version on the left using an STD map, and the version on the right is STD unordered map, which is a hash table. And the code becomes quite a bit simpler, which is nice. How much faster do these versions run? Here are the results. Well, on the left we have the original, and the two new versions are on the right. Okay, a little bit faster, I guess. Are we done? Does anyone have other ideas? What can I do to improve performance? Yes. Prefix operator, okay. Anything else? Well, what's the title of this talk? Profiling. Profiling in games, that's the title. So why don't I run a profiler on it? That's what I did. So I used the Visual Studio Profiler. It's built into Visual Studio 2012 and 13. It shows us some interesting things, actually. If you look here in the source code view, this is the original algorithm that does the linear search. You see the dark red line? It's got 89% next to it. That's telling us that the program spends 89% of its time calling word reader get word. So it turns out the problem is not the linear search, it's the function which fetches the next word from the input. So let's look at the details of that function. Again, we have a dark red line. You see that 86% of the time is spent on a line which reads a single character at a time from an stdif string. This turns out to be an expensive function. So what can we do to avoid it? Well, one simple thing we can try, preload the entire document in memory first and scan through its contents using pointer arithmetic. So on the right there, that's what the new getWord function looks like. It doesn't use ifstream anymore. How much faster does this code run? All right, much better. Here's the new times we get. The original version runs 3 times faster. The other versions are even better. Now, you can play with this code. It's up on GitHub if you really want. But the point is, anytime you ask the question, how do you make your program run faster? Most of the time, the correct answer is use a profile, because there's all sorts of surprises waiting to be discovered. And the thing is, that statement, use a profiler, very easy to say, it can actually mean a lot of different things, as I'm about to show you in this talk. Now, profiling is when you take measurements from a running program, and you can measure all sorts of things. You can measure memory, you can measure network bandwidth, but in this talk, I'm going to focus on CPU profiling. So, imagine this is the source code to your program. You've got a bunch of functions calling each other. When you run it, you can visualize its execution as a series of function calls over time. So on this timeline, you can see, all right, A calls B calls B 3 times, B returns. You get the idea? CPU profiling is all about measuring activity along this timeline. And there are several ways to measure it. One way is by instrumenting the code. This is when you add code to the program so that it measures its own performance. It's an invasive technique in the sense that in order to measure execution time, you actually slow it down because you've added code to it. And that's kind of undesirable. Ideally, you want to take measurements that are as close as possible to your final build. So it should go without saying, don't profile debug builds. There's no point. And you don't want to go too crazy with instrumentation either. Because if you do, that tends to give you lopsided results. Another profiling technique is CPU sampling. This is where, as the program runs, the system interrupts it, say, 1,000 times a second. Could be less, could be a lot more. And each time it interrupts it, checks to see, okay, what's the currently executing instruction at that moment in time? And that's a sample. So in this example, you see, maybe 16 samples ended up in D, 9 samples ended up in B. And from these figures, the profiler can estimate how much time was spent in each function. And there's no need to instrument, no need to recompile anything, which is cool. This technique as well can slow down your execution. It's also invasive, depending on your sample rate. But at least the slowdown will be uniform. All right, so on Windows, there are various sampling profilers available. Here are just a few. The 2 on the left cost money, 2 on the right are free. They all vary in terms of the features that are available for exploring the data. Then you have sampling profilers for games. Now these are proprietary tools. They're covered under NDA, which means I can't really show them to you in this talk, except for a couple slides or that permission. But I can show you the ones up top. So let's look at an example from a game I worked on. So last year I shipped a game called Child of Light. It was a game that ran at 60 frames per second, and it shipped on 6 different platforms. This scene right here was particularly problematic because it had a really high object count. There's a lot of parallax in the background. You've got these floating cities back there, which themselves, each of them is quite expensive. And we had already done a lot of optimization on both code and data, but near the end of the project, this scene still just ran at 55 frames per second on Wii U. So I used Wii U sampling profiler to see if there's anything we could do. Now I can't show you the Wii U profiler, but I can show you VTune, so I'm going to recreate the experience using VTune. The idea is while the game is running, start a capture, let it run for 10 seconds, it's going to collect a bunch of CPU samples. When I stop it, I get these results. And if we zoom in for a closer look, it's taken the number of times each function was hit by a sample, estimating CPU time, and then it ranks the functions from most expensive to least, or how much, according to how much time was spent in each one. And here I filtered the information down to just the main thread. And it turns out the second most expensive function on the list, something called active-visible. If you divide these two numbers, you find that 2.5% of the CPU time is spent in this function. But on Wii U, actually, this number was 10% for this scene. And that's a pretty big fish. It means that if we optimize this function on Wii U, we stand to gain potentially up to 10% of our frame rate back. So that's worth pursuing. Now in VTune, if you double click on a function, it takes you to the source code view. This is really similar to the source code view I showed you in Visual Studio Profiler. Not every profiler has this view though. And right away, this red bar jumps out on the right. It's telling us that among the CPU samples that ended up in this function, most of them occurred on this line. I'm sure you can't read it, but it's an if statement inside a for loop, and it performs 2 checks. Now, in VTune, you can actually expand down to the assembly level. So I looked at the instructions involved with both of those 2 checks. The first one involved some bit shifting and masking. So it was more expensive than the second check. So the first thing I tried was just reverse the order of these two checks performed in the if statement. That change alone saved 0.15 milliseconds per frame on Wii U. So right away we've improved our frame rate by almost 1% with a single change. But still, add to visible was showing up at the top of the list. And something just kind of seems suspicious about that. So I investigated a bit more deeply, found that this function, okay, converts a set of objects to a linked list. The linked list is modified in place, which means it's the same linked list from one frame to the next, just to clear it. And it has this rule where child objects must appear in the list after their parents. And it turns out it was wasting a lot of time making sure of this, because for every object in the scene, it was recursively visiting all of its descendant sub-objects. And for each one, removing it from the list, re-adding it back to the list in a good place, even if that object was already visited from a previous object in the scene. Long story short, there was a lot of waste here, and I was actually very glad to see it, because when you see waste like that, it means there's a nice optimization opportunity. So what I tried is just, all right, let's not bother trying to maintain the same linked list from frame to frame. Let's just clear it and rebuild it each frame. And this paid off. After making this change, add to visible was no longer the second most expensive function, or among the most expensive functions even. It moved way down here, like 100th place, taking a fraction of its previous cost. And that scene now ran at 60 FPS on Wii U, so a huge win that was found thanks to the CPU sampler profile. And it was easy to see the improvement in this case, because in development builds, we can enable this frame rate counter in the top right corner. In Child of Light, the game was pretty obvious, because in that game, the counter tended to be pretty stable. The engine performed pretty much the same work from one frame to the next. So when we measured frame rate, that number in the corner would pretty much stay at 55, 55.1, whatever frames a second. On other games, that's not always the case. A more complex game, like Assassin's Creed Unity, the amount of CPU work done from one frame to the next varies a lot. So if you have an optimization which saves, let's say, half a millisecond per frame, which is excellent, it's not always easy to tell, because you just look at this frame rate counter and you see it's jumping around 27, 31, 29 frames per second. Because of all this activity going on in systems unrelated to what you changed. So for measuring changes in that kind of game, instrumentation comes in handy, because instrumentation lets you measure exactly the section of code that you're interested in. And at Ubisoft, we instrument our code by hand using profiling macros like this one. So this would be a preprocessor macro. It expands to a C++ object on the stack. It samples the start time in this constructor, samples the end time in this destructor. And once we start measuring these functions, there are several ways to display the timings. One way is to display it on screen. So here we have a list of profiling markers, and the green bars represent the total CPU time spent across all threads inside that marker for each frame. It's actually an average, it's averaging multiple frames. So if you know which system your optimization affected, these figures can provide a nice way to measure your optimization without the noise of the activity going on in unrelated systems. So these bars have been around since before I started at Ubisoft, which is more than like 10 years ago. And at some point, for a game I was working on, I wanted more detail than just the averages. So I came up with a different way of visualizing the same information, called the scope tracker. The idea was at certain moments, the scope tracker would dump a detailed summary of what happened in each thread to the debug output. So these were not averages, this is a real timeline of events, what happened during that frame. And you can see the timings of everything I even had a column to track memory and other metrics. I found that really helpful. It was showing me things that I didn't see before. So this was around 2007, I think it was. And around the same time, people on other projects had the same idea. But they actually came up with a nicer visualization of the timeline, which is just, they made a profiler that just shows you the timeline, exactly like the timelines I've been showing you in previous slides, where nested function calls are stacked on top of each other. This tool actually shows you one timeline per thread, which is what's nice about that is if you have holes in the way that you're scheduling tasks among your CPU cores, you can see them in this kind of view. So for example, in this screenshot, there's a big old hole right in the middle, 1 millisecond long, where 3 worker threads are just sitting there idle. So if you're trying to maximize utilization on a multi-core system, it's helpful to see this kind of thing. All right, one limitation of this approach, obviously, is it can only show you timings for the code you've instrumented. If you want to see what's inside, the only way is to add more markers. And that's not always convenient. So for example, in this case, on Assassin's Creed Unity, we had this issue where once in a while, the player would experience these intermittent frame spikes. So you can kind of see it in the video, once per second, there's kind of this hiccup. It's not very pleasant to play. This issue is really hard to reproduce. Like, it took an hour of testing before you even had a chance of seeing the issue happen. But I managed to grab a timeline capture. And it looked like this in the viewer. Those red vertical lines, they show you the boundaries where each frame begins and ends. And you can see the spikes appear as extra long frames. If they're not obvious, I'll highlight them. There they are. When you zoom in, you can see 42 milliseconds being spent during that spike in something called universe component. So I went and I found this marker in the code, but it called a lot of different stuff all over the place. And I could have added markers to break it down further, and I did. But this issue was so hard to reproduce that it would have taken a long time to narrow down the issue this way, because it would have taken several iterations refining those markers. So instead, I attached the CPU sampling profiler to the console as the tester played. And when the issue occurred, I took a capture. And I also instrumented the code with a user marker. That's that long purple bar you see at the top to identify that long task that I want more information about. Not every profiler supports user markers, by the way, but they're pretty handy when you need to pinpoint and report the time section. Then I filtered the CPU samples just to that time. And most importantly, I enabled sampling with call stacks. So instead of just grabbing the current instruction for each sample, the system was actually grabbing the entire call stack at regular intervals. So obviously this technique is more invasive than just sampling the current instruction. It slows down your game more, but it gives you much more detail, because then what you can do is you can browse those call stacks in a hierarchy. So in this view here, at the root, you've got a list of threads, and you can expand any one of them to look inside. You can drill down, see which functions call which other functions, how much time each one takes. And remember, these are filtered just to that frame spike. So it's showing me what's inside. And I quickly saw the majority of the time is spent inside JSON writer. And I also saw the reason why it was called, because I have a call stack. So both the appended code and its cause have been identified. So at that point, modified the game to call this code every frame so that I could study it. And a couple of bottlenecks stood out. So after optimizing those, frame spike went from 42 milliseconds down to 4. And we also made some changes that the spike happened a lot less frequently in the first place, and not once per second like you were seeing in that video. So now I've shown you several ways that sampling profilers let you visualize where your CPU time is being spent. One way that they don't show you, that I really wish they did, is a view called flame charts. The idea here is that since the system is already sampling call stacks at regular intervals, the profiler can actually reconstruct the timeline for you, exactly like the timeline views we've been relying on. And it can do this for every thread without you having to instrument anything. Or maybe if you did instrument things, that would just enhance the view. So that's a view I'd really like to see. If you search online right now, you'll find some blog posts, people exploring the idea. Worth noting, Google Chrome, the browser, it has a built-in profiler for JavaScript that already shows you this kind of flame chart view. And I believe it's also based on CPU sampling with call stacks. So it'd be cool if native profilers would adopt this visualization as well. So, in this talk, we've seen several uses for profiling. There's exploration. We don't know what the problem is, and you're just looking to find out, like we saw in the case of the word count, child of light, that frame spike. You can use a profiler to estimate things, measure what's the potential, expected improvement if you were to make a change. So you know if it's even worth pursuing. Many times, I've had fancy ideas for an optimization I could do, but when I actually measured the relevant code, I realized it really wouldn't have made an impact. So that's good to save you, wasting effort. And you can also just try things and see how that affects your measurements. It's another way to use profiling. If a change is easy to make, just try it, measure the timings before and after. The results may speak for themselves. Like I mentioned, it's not always easy to measure effects. Like in the case of that unsteady frame rate counter, sometimes it can take some effort to find the best way to measure what you want to measure. But at all times, the point of profiling is you want to base your decision on facts and real data rather than trying to guess, because that's how you can get the best results. That's the end of the talk. Thanks for listening. Any questions? Go up to the mic.
Hi, thanks for the nice talk. I was just wondering if you had any tips for going through all the sort of code when you want to find, offending parts. I mean, I know you had the timeline charts, but in a lot of cases, the changes are very small and it's difficult to see with like large code bases.
I wish I knew sort of a recipe you could follow to identify when you look at the profile what's right and what's wrong. Obviously, it helps to know the code. But when you work on a game, you often inherit a game engine from someone else. So you kind of have to make an educated guess in a lot of cases. Can't really give a great answer, but from working on several games over time when things start to look suspicious. Best I can say.
Well, thanks for the answer.
I wonder if you do the same with GPU, like, are you able to see the program under the shader? Like, if you're trying to see if you can make shader work better.
So the question involves GPU profiling?
Yeah, how do you do that?
There's tools for that as well. Last time I did GPU profiling was like 8 years ago. So I pretty much rely on our graphics programmers in that area. You could try Pix for Windows. That's a tool. Run it, gives you a lot of details.
You mentioned a few times developing for Wii. How much time did you say that you put into supporting the Wii throughout your development?
On Child of Light?
Yeah.
First of all, we had a working engine. We started from Rayman Origins. But we did add a lot of features and online stuff. It took one programmer full time throughout the whole project to get it up and running again and maintain it. And near the end, I don't know, maybe a couple programmers working for a month every time.
Did you consider it like a hassle or?
No, surprised. I heard it was a hassle. Maybe it was before I worked on it. I didn't have such a